Hello everyone. Today we are gonna solve some problem from chapter 5, and today we will try to finish chapter 5, and then next session we will start solving some problem using Lagrange in order to derive equation of motion. So let me start with question 5.40, chapter 5. So, which is about the vibration absorber. One of the methods for reducing the vibration of a device, we can use and take advantage of vibration absorber. Suppose we have a system like this, K1, M1, which is subjected to force oscillation. F1 is F0 sine of omega t. So there is a response x1, which is equal to x sine of omega t minus phi. So in order to reduce the vibration of this system M1, we could add a spring mass K2 M2 in a specific way in order to reduce the amplitude of X1 and transfer all the vibration energy and all the vibration amplitude into the mass M2. Basically, we don't care how much M2 will be vibrated. All we have to have is just, we have to make sure the amplitude of mass 1 should be diminished, should be around 0. So what you have to do is just detecting the excitation frequency omega and make it equal to natural frequency of single degree of freedom system for the mass 2. So you have to choose K2 and M2 in a way that the square root of K2 over M2 would be equal to excitation frequency of force vibration, which we normally call omega n22. So the proof for reducing the amplitude of the main mass can be analytically implemented. So for this system, if you derive equation of motion for both mass M1 and M2, for the example I just gave you for reviewing what is vibration absorber, a brief introduction to vibration absorber. And so if you solve this, if you derive this to equation of motion, then you will have basically K1 minus M1 omega squared K2 M2 omega squared K2 minus M2 omega squared K2 minus M2 omega squared amplitude 1, amplitude x2, which is equal to F10, F naught. So if you solve this equation, you will reach to this point that x1 is going to be k2 minus m2 omega squared f naught divided by the matrix Z, which is the using the matrix Z is the Kramer determinant for the, if you use the Kramer approach for solving x1 and x2, the denominator is just nothing but the Z matrix. It's just this equation, the determinant of this equation. This is called Z, determinant of Z. So if you take a look at here in the denominator, so how we could make x1 0, how we could make how we could reduce the amplitude of vibration of the main mass. So all you have to do is just adding m2 and k2 in a way that s square root of k2 over m2 is equal to excitation frequency. So and also this helps you to reduce the vibration of the main mass and vibration of the absorber mass. We normally don't care about how much the absorber mass vibrates. However, the vibration of absorber mass is K2 minus, for this system, M1 omega squared F naught over determinant of matrix Z. So this was just an introduction to the problem, and let me just read the problem. 5.40. So there is a system basically there is an unbalancing the system which create vibration in our main mass W1 or M1 main mass, and this is basically she's attached. The main mass is connected to the ground through two stiffness with the two spring with a stiffness of 1/2 K1 and 1/2 K1. So in order to reduce the vibration of the main mass, we could add a vibration absorber, just a spring and mass M2 or W2. So for the system shown here, W1 is given 200 pounds and the absorber weight is given to you 50 pounds. If W1 is excited by a 2-pound inch unbalanced rotating at 1800 revolution per minute, determine the proper value of the absorber spring K2 and what will be the amplitude of W2? So basically, we have a system like this, and we want to find K2. And for an absorber, you know that K2 can be easily obtained just by square root of K2 over M2 is equal to excitation frequency. But for X2, you need to have equation of motion and then solve it. But for K2, it's very easy because we know that for the absorber mass K2 over M2, it should be excitation frequency. It's very easy. Can be done without deriving equation of motion. However, for X2, you need to have equation of motion and then solve it in order to find the X2. So in order to derive equation of motion, suppose that this is X1 and this is X2, and you could take advantage of second Newton's law. So for deriving the equation of motion, so for the mass 1, because we have a 2D graph freedom system, for the mass 1, summation of momentum is equal to m multiplied by x double dot. M is just non-rotating mass, non-rotating is consists of non-rotating mass and rotating mass. That's why it's better to write like this. So M1 minus unbalanced mass x double dot 1 plus M not rotating unbalanced mass x double dot not. So let me describe it to you, because this is M naught. If you take a look at here, this is M naught. So the displacement of this is x1 and this is x naught. So if I call this radius r and this angle as theta, I can write x1, x naught is equal to x1 plus r sine of theta. So therefore, you could easily take derivative x double dot, and theta is omega t. X double dot naught, therefore, is going to be x double dot 1 minus r omega squared sine of omega t. So for the mass 1 in upper system, there is the unrotating mass and rotating mass m naught. M1 minus m naught. So the acceleration is, which is applied to the on-rotating mass, is x double dot 1 here, and the acceleration applied to the unbalanced rotating is x double dot naught. So if you plug in this relation we obtain for x double dot naught and x double dot 1, we could write the acceleration in terms of only x1. So if I further simplify this system, so in the right hand side, m1 minus m naught x double dot 1 plus m naught over x double dot 1 minus r omega squared sine of omega t. This is x double dot naught. So which is equal to, so if I displace the whole system, the mass 1, toward downside, these two springs will oppose the motion, or toward upside. So there are two opposing springs here. So therefore, on the right hand side, summation of forces applied to the mass 1 would be minus 2 k1 over 2. The stiffness of the two springs is k1 over 2 multiplied by x1. And also we have a absorber mass and k2. So you have to write minus k2 x1 minus x2, because the spring k2 is connected between the mass 2 and mass 1. Therefore, we have to take care of relative displacement between the two. If I further simplify this equation, therefore I will reach to m1 x double dot 1 plus k1 plus k2 x1 minus k2 x2, which is equal to m naught r omega squared sine of omega t. You could call this term f naught, unbalanced amplitude force. This is the equation of motion for the mass 1, basically. And for the second mass, absorber mass, you could then apply summation of forces, second Newton of law, m2 x double dot 2 similarly. Therefore, if I displace the mass 2, there is a spring that opposes the motion, minus k2 x2 minus x1. Therefore, m2 x double dot 2 plus k2 x2 minus k2 x1 is going to be 0. This is the second equation of motion. Therefore, we could derive the matrix format x double dot 1 x double dot 2 plus k x1 x2 is going to be f naught sine of omega t 0. So therefore, if I further simplify it, it would be k minus m omega squared multiplied by x1 x2 if I consider harmonic oscillation. Therefore, x1 and x2 would be, if I call this matrix A or Z, it would be A minus multiply by f0 and f. Then you could find amplitude of x1 or x2. For the first part, we were supposed to find the K2 for the absorber. For designing absorber, always you have to pick up the excitation frequency and make it equal to natural frequency of absorber mass only, which we consider it as a single degree of freedom system, which is become K2 over M2. This is how you have to design absorber. So K2 therefore would be M2 omega squared. M2 is W2 over G omega squared. Therefore, K2 50 pound G, you have to go through the table and find the corresponding G for the inch unit, 386 multiplied by. So the excitation frequency is based on revolution per minute, RPM. You have to change it into the radian per second. So 2 pi multiplied by 1800 RPM. We have done here for several times. So I just wrote the formula for. Therefore, the stiffness would be 4,600 pound-inch. So the stiffness, if we choose K2 like this, therefore always X1 would be 0, as I proved in the first part of the session for today. Analytically, if you solve it, X1 is always 0. Because numerator will be 0 if you choose omega as K2 over M2. So apart from K2, which we were supposed to design for absorber mass, we were supposed to basically find the X2, the amplitude of absorber mass. So if we designed like this for the absorber mass, all the vibration force will be transferred to the absorber mass. So therefore here absorber force would be equal and opposite to excitation force amplitude. So absorber force K to M2, absorber force is nothing but K2 X2 is equal to excitation force F naught, force amplitude M E omega squared. Therefore, X2 would be M E omega squared over K2. And I could write, even though I have the value of K2, just let me simplify it further before inserting any non-variable, non-parameters. So M naught here, M naught E omega squared, K2 is M 2 omega squared, right? So I can therefore cancel out omega squared. Therefore, I can write amplitude 2 would be M naught eccentricity E divided by M2. Since I don't have M naught and M2, rather I have the weight, I could write W naught over G multiplied by eccentricity over W2 over the G. If you take a look at the question given, the unbalanced rotating is given in terms of 2 pound inch, 2 pound. So you have to draw a conclusion that the multiplication of weight and eccentricity is given to you. So 2 pound inch is W naught E. If you take a look at here, I can further simplify by canceling out G from numerator and denominator here. I can therefore further simplify this equation for and solve for x2 W naught E divided by W2. The numerator is given as 2, denominator W2 is 50, 0.04 inch. This is the amplitude of the absorber mass. So if you have any question, just let me know. So next problem would be 5.42. There is a rotating system like this. So this mass ID, which is rotated around point O, is connected to the mass 1 using 4 spring K. This is I, and this length is 2A. There are basically 2 rotating masses that independently can rotate. Therefore, we are facing with the system with 2 degree of freedom system, and let me read the problem 5.42. It says a flywheel with moment of inertia I. This is a flywheel basically. This is the flywheel, and so this is a flywheel which has a absorber, which has a torsional absorber with a moment of inertia ID, free to rotate on the shaft and connected to the flywheel by 4 springs of stiffness K pound per inch, as shown here. Set up the differential equations of motion for the system and discuss the response of the system to an oscillatory torque. So we are supposed to find the response. Therefore, we must derive equation of motion. Since we are facing with a system with 2 degrees of freedom, we have to come up with 2 equations of motion, one for the flywheel and the second for absorber mass. So since we are facing with a rotational system, we have to take advantage of Euler formula for deriving the equation of motion. So therefore, for the mass one, if I rotate the I, basically this point will come to this point, and if I draw it here, there is a basically so the displacement of this point would be, this is 2a and this would be a. So here x a theta, x would be a multiplied by theta. Or I could say, if I rotate the flywheel and this point, or you could say this point will come to this point, so you could calculate the deformation at each spring. So summation of motion, summation of momentum around point O for the mass one is equal to I theta double dot. There are 4 basically spring, and each spring, if you take a look at here, each spring is connected between the 2 points, mass 1 and mass 2, this point. So we have to take advantage of, we have to calculate relative displacement, and therefore we have 4 springs. So you could consider this clockwise as positive direction for the momentum. So this force, this 4 spring will opposes the motion like this, and which create basically so this, the direction of these 2 is different from the direction of. So if I rotate the flywheel clockwise, the upper 2 spring will opposes the motion, and also the lower 2 spring will also opposes the motion like this. If you take a look at here, and these 4 force will create counterclockwise momentum around point O. Counterclockwise momentum. So, and this is the arm distance. So therefore I'll have 4 spring, 4 spring, 4K. Each spring is subjected to relative deformation of theta 1 minus theta 2 multiply by A. A multiplied by theta 1 is displaced with 1. So x1 is A theta 1, x2 is A theta 2. So Kx is the force, basically. This is the force. Multiply by the related arm, which is A, and plus, if there is a external oscillatory momentum like this, m naught sine of, if any external force existed. So all the momentum would be equal to I theta double dot 1. If I simplify this equation, I'll have therefore I theta double dot 1 plus 4k theta 1 minus theta 2 a squared equal to m naught sine of omega t. This is the first equation of motion for the flywheel, and similarly you could derive equation of motion for the absorber mass, torsional absorber mass. Summation of momentum applied to the absorber mass is going to be I d theta double dot 2. If the absorber mass wants to rotate, and this force spring will oppose the motion, therefore again we have minus 4k theta 2 minus theta 1. This is the force multiplied by arm, which is equal to I d theta double dot 2. Therefore, the equation of motion for the second mass is I d theta double dot 2 plus 4k theta 2 minus theta 1 is going to be multiplied by a squared is going to be 0. So the second step or next step would be transferring the linear equation of motion into a matrix format. For I'll have I 0 0 ID theta double dot 1 theta double dot 2 plus 4k a squared minus 4k a squared minus 4k a squared, and here the last array is 4k a squared multiplied by amplitude theta 1 amplitude theta 2 would be equal to m naught external momentum, m naught sine of omega t, and 0. If you solve this equation, you will reach to this point that theta 1 is going to be 4 minus n lambda divided multiplied by m naught sine of omega t divided by n lambda squared minus 4 1 plus n lambda plus 15. We have used basically n and lambda in order to simplify the calculation procedure. So for the sake of simplicity, we have just used assume lambda is just omega squared and divided by k a squared, and n is nothing but the ratio of mass moment of inertia of the absorber mass divided by I. The only reason for just assuming these two parameters just for sake of simplicity, and we have simplified the answer in terms of lambda and n. And if you take a look at here, the mass one is our main mass. We have in the absorber design, we always want to minimize the amplitude of the main mass, which is our focus, which is our aim. So if you take a look at the numerator, theta 1 is the response of the amplitude. So how we could basically minimize or make the amplitude of the main mass 0. So theta 1 can be 0 if and only if 4 become equal to n lambda. Therefore, this is mathematically translation of designing absorber. We just merely and just taking a look at to the numerator of the response. So it is basically satisfy this relation we have used in the first part of the today introduction, K2 or M2. In another way, when you make the numerator of the x1 or theta 1 0, you are basically or indirectly trying to put natural frequency of only absorber mass equal to excitation frequency. So these are basically the same. So if 4 is equal to n lambda, lambda was omega squared I over k a squared basically 4 is n lambda and lambda is 4 divided by n, therefore lambda would be lambda is omega squared I k squared 4 divided by n, id over I, which is going to be 4i id omega squared I k squared 4i id. So you could easily cancel out the I from both sides. Then omega squared is k4a squared over id. Therefore, excitation frequency is going to be 4k a squared id. If you choose k in this way, that satisfies this equation, therefore the main flywheel, the main mass, the deformation or the rotation of the main mass would be 0, and you can also go for rotation of theta 2 and solve for theta 2. So we were supposed to basically derive the equation of motion and discuss the response of the system to the oscillatory torque. So if you have any specific question, you can ask. So let me start the solving next question. For 24, it's very easy. There are some information, L1, L2. So we are basically modeling an automobile with 2 degree of freedom system. K1, K2, so this is basically chassis of an automobile, and the mass is concentrated at center of gravity at this point, and this is L2 and this is L1. A stiffness K1 and K2 is given. K1 and K2 is given, L1 and L2 is given, and radius of gyration about center of gravity is given 4 foot, and the W also is given. Determine the normal modes of vibration and locate the node for each mode. So for finding the normal mode, we have to derive equation of motion and solve for natural frequency, and then at the end we can easily obtain the normal mode. So this is the system we are trying to. So I can further simplify. So there is a chassis, we could show it by a bar like this. So center of gravity, you see, as soon as we install the spring and release the automobile or the mass, it will be move and be stationary at the static equilibrium position. So here, if it is a static equilibrium position, and then the chassis or the bar can have 2 independent motion, one vertical and one rotation. So in order to derive equation of motion, we just simply apply vertical motion. So X, and then from that point, we could also rotate the system theta. So the 2 spring will oppose the motion. This deformation is X plus L2 theta. This is L2 theta. This length is L2 theta, and the total deformation applied to the right spring is nothing but X plus L2 theta. And the total deformation applied to the left spring is just this length. Is X minus L1 theta, because this length is L1 theta, and this is going to be spring force for the left spring, and the spring force for the right spring would be K2 X plus L2 theta. Therefore, you could easily apply second Newton of law. So summation of momentum applied to the mass, the vertical motion, is M x double dot. There are two springs will oppose the motion, so minus k, k2, the right spring x plus L2 theta. The left spring will oppose the motion, minus k1, x minus L1 theta. So there is a rotational movement also. Summation of momentum around point center of gravity is I around center of gravity theta double dot. So you could assume positive direction clockwise. So the left spring will create clockwise momentum. However, the right spring will create counterclockwise momentum. So you could easily write the summation of momentum. The left spring positive clockwise momentum, K1 x minus L1 theta is spring force multiplied by arm, which is a L1 minus the spring force at the right spring will create counterclockwise momentum. That's why we just inserted negative L2 theta multiplied by the arm L2. If I further simplify the two equations, I see theta double dot. I can then simplify into a matrix format. M naught 00J x double dot theta double dot plus the stiffness matrix K1 plus K2 K2 L2 minus K1 L1 K2 L2 minus K1 L1 and K1 L1 2 plus K2 L2 squared x theta is going to be 0, 0. If you solve it and for natural frequency, therefore omega squared, omega n squared would be 36.57. Therefore, the first natural frequency would be 6.047 radian per second. And the second natural frequency squared would be 69.53. And the second natural frequency would be 8.34 radian per second. So if you choose one row from the equation of motion in the matrix format and insert the natural frequency, you can easily find the corresponding mode share. The first mode share is minus 10.9. You could give a denominator 1 foot per radian. And the second natural mode shape is x over theta is 147 foot per radian. You can give a denominator 1. So here for the first mode, x over theta, the first mode shape if we have a positive rotation, there would be a negative 10.9 foot displacement of the system. So positive rotation, and negative deformation of 10.9 for positive 1 radian. Or you could say if you could say positive displacement for minus 1 radian deformation. So negative 1 radian. So center of gravity will displace plus 10.9. The downside, we consider positive direction. So if we continue this, we'll reach to the node. And for the second mode shape, however, for each positive radian, there is a positive 1.4 foot displacement. So C is here, positive rotation, 1 radian. There would be a positive 1 radian. There would be a positive 1.47 foot, or you could say negative 1 radian, negative 1.47. So negative 1 radian would be negative minus 1.47. So this is how you can obtain the natural mode shape. So 5.24, we are done with 5.24, and if you have any question, just let me know. Otherwise, we will go for 5.29. So these are several hints for this question: 5.40, 42, and 49. Because we don't have time to solve all the problem for this session. 5.29. We already solved several problems to find the natural frequency and mode shape. So 5.29 is also similar to we have already solved. Determine the natural frequency and normal modes of the system shown here. It's very simple linear mass spring, very simple. Just I'll give you the final answer. A simple linear mass spring system, the basic problem which you could have M1, K1, M2. So this can be displacement for mass 1, displacement for mass 2. So there is a external oscillation here, F1, which is F naught sine of omega t. Determine the natural frequency and normal mode. So all you have to do is just deriving equation of motion. You have a spring, you have masses, and then once you have the response, you can plot the response based on the omega over omega 1,1, which you are asked for. As soon as you obtain x1 and x2, you can easily plot them based on omega over omega 1,1, x1 and x2. Omega 1,1 is just the natural frequency of this system only. Omega 1 is K1 over M1, which is different from the natural frequency of the system. And omega 1, 2, 2 is also K2 over M2, which is also different from natural frequency of the two systems. These are not the same. So if you use the second Newton's law, you will reach to this point. For deriving equation of motion, M1, 0, 0, M2, x double dot 1, x double dot 2, plus K1 plus K2 minus K2 minus K2, K1, x1, x2, f naught 0, sine of omega t. And therefore, x1 and x2 would be a minus k minus m omega squared multiplied by f0. So this is 529, and the next problem would be 555. So the 555, the two uniform rigid bars. So there are basically two uniform rigid bars like this. K2, K1, L1, L over 4, 3 over 4L, K1, this length is also given as L over 4. This is L over 2, and this is L over 4. So the two uniform bar here are of equal length but different masses, M1, M2. M1, M2. Determine the equations of motion and natural frequency and mode shape using matrix method. The method we have used so far is just called matrix approach. And since we are dealing with rotational system, all you have to do is just applying Euler formula for two bars. So if I displace the rigid bar 1 toward up, if I have a counterclockwise and I consider it as a positive, so this is the spring will oppose the motion, and the spring force is nothing but K 3/4 L theta 1 minus 3/4 L theta 2, because this point, the spring is connected between the two and there is a relative motion. So this displacement would be 3L/4 multiplied by theta 1, and this is going to be 3/4 L multiplied by theta 2. So the relative deformation would be x1 minus x2. L theta 1 x1 minus x2. And you can easily apply the Euler formula to derive equation of motion. Summation of momentum around point A is going to be mass moment of inertia around point A, theta 1 is equal to theta double dot 1. Therefore, since this force creates clockwise momentum, we assume counterclockwise positive, therefore there is a negative momentum here, negative 3/4 K1 L if I factor out this term from the above relation. Therefore, I'll have theta 1 minus theta 2. So this is the force multiplied by the arm. So the arm is, this is the force. This is the force and this is the arm, which is 3/4 multiplied by L. Therefore, the first equation of motion would be I1 theta double dot 1 plus 9/16 K1 L squared theta 1 minus theta 2 equal to 0. And we know that I around point A is equal to I around point C plus M d squared. D is this distance on the basis of parallel axis theorem. Therefore, I around point A for the mass one would be 1/12 M1 L squared plus M1 L/2 S squared, which is totally would be 1/3 M1 L squared. The mass moment of inertia around point A. And similarly, if I derive equation of motion for the lower bar, so for the lower bar, so if I consider the clockwise as a positive rotation, therefore the upper spring will oppose the motion and the lower spring will also oppose the motion. So here summation of momentum around point O is equal to I2 theta double dot 2. Again, this force is nothing but 3/4 K1 L theta 2 minus theta 1, and this force is K2 L over 2 theta 2. Because if you take a look at here, this displacement is L over 2 and this is theta 2. So x2 would be for the x2 for the lower bar is L2 divided by 2 multiplied by theta 2. And similarly, you could find this force, which is the same for the above bar, the reaction and action force. These two forces, however, will create counterclockwise. Therefore, we are facing with two negative 3 over 4 K1 L multiplied by theta 2 minus theta 1 multiplied by 3 over 4 L minus K2 L over 2 theta 2 divided by L over 2. So this is the force R. This is the momentum, which is equal to I2 theta double dot 2 . If you insert and write the equation of motion in matrix format, therefore you will have I1 0 0 I2 theta double dot 1 theta double dot 2 plus 9 over 16 K1 L squared minus 9 over 16 K1 L squared minus 9 over 16 K1 L squared and 9 over 16 K1 L squared plus K2 L squared over 4 theta 1 theta 2 is going to be 0. So we know that by assuming harmonic response, theta double dot 1 theta double dot 2 would be minus omega squared theta 1 and theta 2. If you plug in the equation above, you will have 9 over 16 K1 L squared minus I1 omega squared minus 9 over 16 K1 L squared minus 9 over 16 K1 L squared 9 over 16 K1 L squared plus K2 L squared divided by 4 minus I2 omega squared. So multiply by theta 1 theta 2 is going to be 0 0. So all you have to do is just in order to determine the natural frequency, all you have to do is just calculating the determinant of this matrix and make it equal to 0. This equation will give you the corresponding two natural frequencies, and then you could go for the natural mode. So therefore, the determinant of k minus m omega squared matrix should be 0. Then 9/16 k1 L squared minus I1 omega squared 9/16 k1 L squared plus k2 L/4 minus I2 omega squared minus 81/256 k1 squared L power 4 equal to 0. We already obtained I1. Similarly, we could obtain I2, which is I prime I to the point center of gravity plus md squared according to the parallel axis theory. So therefore 1/12 ml squared. However, this time d is not L/2, is rather L/4 squared. Therefore, the I2 would be 7/48 m2L squared. So just insert these two mass moment of inertia, then simplify the equation, and you will reach to this point: 7/144 omega to the power 4 minus 271/768 k/m omega squared plus 9/64 k/m squared equal to 0. If you consider omega squared as a lambda, then lambda 1 is going to be omega n squared. 1 is going to be 6.835. Therefore, the first natural frequency is going to be 0.650 square root of k1/m1. And it is assumed that k1 is equal to k2 and m1 is equal to m2 is equal to m equal to k. So 650 k/m. And the second natural frequency, lambda 2, is omega n2 squared, is obtained as 0.4227. Therefore, the second natural frequency would be 2.614. The first natural frequency is so here omega n2 basically is 50 K over M. So we made a mistake here. So the first natural frequency is going to be 2.614 K over M. So, and therefore, you can go for the normal mode shape. The normal mode shape, the first mode theta 2 over theta 1 would be 0.615, and theta 2 over theta 1 second mode would be minus 1.549. In order to obtain the normal mode shape, you have to take one row of the equation of motion in matrix format and just insert the natural frequency into the omega. This question is very important, 5.55. And this next problem would be 5.57. There's a bar, the mass moment of inertia, the mass center of gravity is located here, and this is L1, this is L2, and basically this is attached to the ground through these two springs, K1 and K2. For the system shown here, choose coordinate x1 and x2 at the end of the bar and determine the type of coupling this introduces. So basically we are given the displacement of the end of the uniform bar, and based on this coordinate we have to come up with equation of motion and then see what type of coupling exists in the system. So if you choose different coordinates, for example, if you choose the linear translation and rotation around point C, center of gravity, you will come up with a different matrix for the stiffness compared to when you come up with a equation of motion using coordinate x1 and x2 at the end of the deformation at the end of the bar. So for deriving equation of motion, so let's say this is the first place of the uniform bar, and C, center of gravity, will go here, x of C, and rotate like this. So this is basically x2. This can be called as x1. Okay, we have to use x1 and x2 to derive equation of motion. So if you displace the uniform bar toward up, this spring force, these two springs will oppose the motion. So summation of momentum. So in order to derive equation of motion using coordinate x1 and x2, let me start writing equation of motion using center of gravity coordinate for the sake of simplicity. And then as the next step, I will go for writing the equation of motion in terms of x1 and x2 using trigonometric formulation. So summation of momentum applied to the system at point C is going to be m center of gravity x double dot c for the pure linear motion, right? It's nothing but minus left spring x1 simply, and right spring minus k2 x2, right? Before further simplify the system, I can say that this is given as L1, right? And this is given as L2. And in this basically triangle, if I take a look at here, I can say that if I have, so let me simplify it here. So if I have a triangle like this, if this side is B, if this side is A, and this is A and this is L2, whenever this angle is 90 degree, I could say that A over B is equal to L2 over L1 plus L2. Therefore, in our question, A is XC and B is X1. So take a look at here, you will see that here basically, if you take a look at this triangle, so this length is B and this small length is A, right? So therefore, A over B is XC, this is XC, basically. This is XC minus X2. XC minus X2 divided by B. B is X1 minus X2. X1 minus X2. So A over B is equal to L2 over L1 plus L2. Therefore, when you say XC minus X2 divided by X1 minus X2 is equal to L2 over L1 plus L2, therefore you could say XC is X2 plus L2 X1 minus X2 over L1 plus L2. All you have to do is just insert XC in the above equation of motion and simplify the equation. Therefore, minus K1 X1 minus K2 X2 would be M X double dot 2 plus L2 over L1 plus L2 X double dot 1 minus X double dot 2. Further simplify of this equation gives me ML2 over L1 plus L2 x double dot 1 plus m L1 over L1 plus L2 x double dot 2 plus k1 x1 plus k2 x2 is going to be 0. This is the equation of motion, and for which describe the linear motion. However, we are only asked to determining the type of coupling that this system introduces. So if you take a look at here, since we have both x1 and x2 in the equation, in one of the equation, in one of the row of the matrix format, this is only one equation of motion for linear motion, right? So in one equation, I can see x1 and x2. That's why I could say there is a coupling between x1 and x2. There is a static coupling, and there is a, since we have x double dot 1 and x double 2, there is dynamic coupling as well. So dynamic coupling is also existed. The system is both statically and dynamically coupled. So, and then for last question, 5, very simple, 5.62. Very simple and just linear. Motion, you are supposed to determine the matrix of equation for the problem 5.62. So there is a system like this. We already solved this type of problem. K1, M2, M3. So K2, K3. M2 is also connected to the wall through K4, and M1 is connected to the M3 through K3. This is X1, X2, X3. If you take a look at here, there are 3 masses. That's why we could say we are dealing with 3 degree of freedom system. Determine the matrix equation. So we are supposed to derive equation of motion in the matrix format. So all you have to do is just take advantage of second Newton of law for each masses. Summation of forces applied at mass 1 is going to be m1 x double dot 1. So if I displace the mass to the right, this spring will oppose, and this spring will oppose the motion, and also the mass 1 is connected to the mass 3 through spring K3. So this would be minus K1 x1 minus K2 x1 x2. Why? Because K2 is connected between the 2 point. So that's why you have to consider relative displacement. For K3 also, the spring K3 is connected between the 2 point M1 and M3. You have to calculate the corresponding relative displacement minus K5 x1 minus x5 for each mass, it is better to draw a free body diagram. K1, X1, K2, X1 minus X2, K5, X1 minus X3. So similarly, if you draw free body diagram for mass 2 and mass 3, the second and third equation of motion would be K2 minus K2, X2 minus X1, minus K4, X2, minus K3, X2 minus X3. And similarly, for the third mass, summation of momentum is going to be equal mx double dot 3, which is going to be minus K3 minus K3, X3 minus X2, minus K5, X3 minus X1. So you could draw, you could put the equation of motion in matrix format. So M1 0 0 0 M2 0 0 0 M3 multiplied by X double dot 1, X double dot 2, X double dot 3 plus a stiffness matrix K1 plus K2 plus K5 minus K2 minus K5 minus K2 K2 plus K3 plus K4 minus K3 minus K5 minus K3 K3 plus K5, a stiffness matrix X1, X2, X3 is equal to 0. This is how we come up with equation of motion. So this is basically at this point we have finished chapter 5, and in the next session we will derive equation of motion using Lagrange approach, which is very important. So see you next session.